3.6. Related rates. Okay, related rates is pretty much the word problem application of implied differentiation, which is, where we find this thing of dy dx equals, some function. And what we're going to look at is, given some change of x, how does that affect some change in y? And that's kind of the goal here. So a lot of these tend to be word problems. A little bit of prior knowledge might be needed. For the most part, I will say if there's any sort of geometrical formula, if one of these ever come up on a quiz or an exam, you'll be given the formula, but we'll kind of walk through a couple of these. Given the area of a circle is pi r squared, how fast is the area changing? If the radius is 4 and changing at a rate, radius is 4 inches, I should say, 4 inches. And it's changing at a rate of 1.5 inches a second. Okay, so really the thing to kind of recognize is what variables we've been given and what we're looking for. So we've been given the radius r is 4 inches, and we've been given this rate of the radius per second. So that would be dr dt is this 1.5 inches. What we want to know is how fast is the area changing. So the unknown that we're looking for is dA dt. Okay, so now that we have this, this kind of lets me know a couple things, which is one, what variable am I going to take the derivative with respect to? Because that's always going to be that denominator here. Since we're given this rate of inches per second, that means we're looking at a derivative with respect to time. So I'm going to take my function and take a derivative of this with respect to t. Okay, so technically speaking, none of my variables here match up, so we're going to have a lot of these chain rules happen. So technically, the derivative of a is just 1, and since the variables don't match, we're going to have dA dt. Now, one thing to be careful about, pi is not actually a variable, pi is a constant, so we're just going to take that out. And then the derivative of r squared is just 2r. And the derivative, since the variables don't match here, we're going to have this chain rule of dr dt. Okay. So doing a little bit of simplification here, we have 1 times dA dt, so that's just dA dt. And then just simplifying this a little bit, we have 2 pi r times dr dt. So we've done the implicit differentiation, which means that at this point, I should have everything I need to just plug in and solve. So the thing we're looking for, dA dt, that's that right there. And we need to plug in, we need something for r. Well, we have that r is 4 inches. And we also have a value for dr dt. So my unknown, we're going to find, and then every other variable, including these little chain rule derivatives, we have a number that we can just plug in for. So this is going to tell me that dA dt is just 2 pi. R here is 4 inches. And dr dt, that's 1.5. So we have that dA dt. So we're just going to throw that into a calculator. 2 times pi times 4 times 1.5. Gives us 37.699. So we'll just say that's dA dt in this case is 37.7. So here's kind of an application of a implicit differentiation. We were able to compare, if you think about a circle, this is how fast the circle is growing in size, and this is how fast the circle is growing in terms of area. Any questions on this example? Okay. Let's do another one. Let's do a business example. Given r of x is equal to 8x, a revenue function, and c of x is equal to 0.07x squared plus 0.2x plus 70. Where x in terms of thousands of units, and technically both r of x and c of x are in thousands of dollars. Okay. If the rate of production, actually, no, let me type these out. Is increasing by 1,000 units a day. Find the rate of profit at 26,000 units. Okay. So first we need to find our profit function. So my profit in general is the revenue minus the cost. So my profit here is going to be my revenue, which is 8x minus the cost of 0.07x squared plus 0.2x plus 70. So that's going to tell me that my profit here is going to be negative 0.07x squared plus 7.8x plus 70. And remember, since x is in terms of thousands of units, so if the number of units is increasing by 8,000 a day, that's dx dt is going to be technically, if we remember, since x represents 1,000 units, technically dx dt is going to be 8 over 1, or just 8. Because technically it's, 8,000 units for one day. So 8. And x is 26, because remember, x is representing thousands of units. And we want to find the rate of profit. So dp dt. Okay, so this is my unknown. So once again, we're going to take a derivative with respect to time. And honestly, for a lot of these word problems, when we're doing these differentials, these implicit differentiations, usually what we're doing is we're taking derivative with respect to time. Okay, so working this all out. First, we have the, I apologize, 70 should have been, thank you, 70 should have been negative because we were subtracting it. Thank you. Yeah, 70 should have been negative there. Okay, so working this out, the derivative of just p as a variable is 1. And since the variables don't match, we have our chain rule of dp dt. In a lot of the other examples, we would have written this as like p prime. I really like to write this using the Leibniz notation because that really kind of lets me know that we're talking about a rate. Okay. So since none of these other variables match up, every time we take a derivative here, we're going to have this chain rule. So 2 times negative 0.07 is going to give me negative 0.14x times, so the variables don't match, so we're going to have a dx dt plus the derivative of 7.8x is just 7.8. And then this chain rule of dx dt. And then technically the derivative of negative 70 is just 0. So just simplifying, we have the dp dt is equal to negative 0.14x dx dt plus 7.8 dx dt. Okay, so working this out. dp dt, that's my unknown. We know that x is 26, so I'm going to plug that in here. And dx dt is 8, so I'm just going to plug that in here and here. So I'm just going to plug that in. So dp dt is negative 0.14 times 26 times 8 plus 7.8 times 8. Okay, so working this all out, you end up getting 33.28. Now here is where we need to talk about units. So we have a number, once again, what does this number represent? So remember that revenue and profit were both in terms of thousands of dollars. And X is in terms of thousands of units. And it was kind of implied here, but T was in terms, I could have written this, T is in terms of days, right? So dP dt is the amount of profit we make in a day. So profit is going to be the difference of R and C, which are both in terms of thousands of dollars. So what we're effectively seeing is a profit of 33.28, technically $1,000 per day. And this time we're going to keep the 1,000 because when do we cancel out those thousands? If we had something like, 33.28, if we were talking about $1,000 over 1,000 days, which would be silly, that's almost 3 years. If they both have 1,000 in them, that's when you can cancel out the 1,000. But here we're talking about thousands of dollars for one day, so we can't cancel that out in this case. So we do need to keep that 1,000 as part of our interpretation. Okay. Any questions? Let me kind of zoom this out one more level. All right, so here's an example where we did have some business example, basically. And just really, I would say the implicit differentiation, the actual implicit differentiation are usually a little bit easier than some of the ones we were dealing with in the last section. Usually the hard part is just kind of interpreting where am I plugging in and what are the units of my final answer. Okay. Questions before I move on to the next example? Okay, so we have in the past looked at a lot of price and demand functions as an example of just a linear function. And I said that we were going to look at some examples when they're nonlinear, and this is going to be that case. So given a price demand function of 3x squared 3x squared plus 4xp plus 30p squared is equal to 37,925. Where X is just the number of units sold, and P is going to be the price. Okay, a lot of text I'm about to throw at you. Let me type this up. Okay, if the price is increasing at a rate of $2 a month, and the price is $25. Find the change in demand at 65 units sold. Okay. So, kind of looking at what we've been given. We've been given a price here of $25. We've been given the change in price, which is increasing, so that's going to be a positive. So dp dt is that $2 a month. And we were also told the number of units, which is x, which is 65. We want to find the change in demand, so the thing we're looking for, my unknown, is dx dt. Okay, so here are kind of all the variables we have set up. The things we're looking for here are change in demand. So we want to take a derivative with respect to t. And we've also kind of implied here that t is in terms of months. So first thing I'm going to do is just take my equation. Oops, 37925. And we are going to take a derivative with respect to time, t dt. So once again, none of these variables have a t in there. So for each one of them, we're going to have this chain rule. Okay, so once again, color coding these. Red first. So the derivative of 3x squared is just 6x. And since the variables don't match, we're going to have this chain rule of dx dt. Plus. All right, so for the next function, we need to break this down using the product rule. So the derivative of this first function is just, well, the derivative of 4x is just 4. And since the variable does not match our derivative, we need to have a dx dt for the chain rule. For my second part, p, the derivative of just the variable p is 1. And once again, p does not match my derivative, so we're going to have a dp dt. Nicer. So, doing the product rule. Says we're going to take the first derivative, so 4 dx dt times the original second function, so times p, plus the original first function, 4x, times the second function's derivative. So it's just 1 times dp dt, so I'm just going to write that as dp dt. Okay, so we've worked out the middle function. Then the last piece. The derivative here, 2 times 30 gives me 60 t. And the variable does not match the derivative, so we have this chain rule of dp dt. And the derivative of a constant is always 0. Okay, quick second for people to kind of write that down. Any questions on this so far? All right. So working this out, all we're doing is we're just kind of plugging in. So we have P. So every time I see a P, there's a P there and a P there. We have dP dt. So there's dP dt, dP dt. And then we also have X. I've run out of colors here, so just do wavy black line. So there's an X here and an X here. So the goal is once I plug in everything, I should have everything I need except for the two unknowns. They're the same thing, but these dx dt's I have right here are going to be left as a variable, excuse me, that we need to solve for. Okay, so we're just going to plug this in. So we're going to have 6. X here is 65 times dx dt plus 4. I'm just going to put this p, I'll just leave it as is. I'll just leave it exactly as dx dt times p, which in this case is 25, plus 4 times x, which is 65, times dp dt, which is 2. And then lastly, we have 60 times the price of 25 times the change in price dp dt, which is 2. Okay. So the calculus part is done. This is really an algebra problem from here on out. So just kind of working this out. We have 6 times 65 gives us 390 dx dt. I'm just going to multiply those together. 4 times 25 gives me 100 dx dt. Four times 65 times 2 gives me 520. And 60 times 25 times 2 gives me 3,000. Okay. So just combining my like terms here, these are both dx dt, so we can add those together to give me 490 dx dt. And then 3,000 plus 520 gives me 3,520 equals 0. Okay, so working this all out then from here is we're just solving for this as a variable. So I'm going to subtract over 490 dx dt is equal to negative 3520. And the last step is we're just going to divide by 490. So that gives me that dx dt is equal to negative 7.18. And then in terms of units, so X was in terms of units, T is in terms of months, so it's negative 7.18 units per month. And this actually makes sense, right? We said we increased the price, which means, and this is what we saw right here, we saw an increase, a decrease in demand. And that's what we just saw, right? Because we increased the price by $2, this is telling us that the increase in price cost us a little bit more than $7, sorry, not $7, 7 units a month. Okay. let me kind of zoom out one more time. Any questions on this example?
Mr. Professor Brown.
Go ahead.
Okay, just to make sure on that, the second step right here, where it's 3x d over dt, and then
Mm-hmm.
3x squared plus 4xp plus 30.
Gotcha.
So on those, on the whole numbers, you would multiply them by the power, right?
Correct.
Okay.
Yeah, so all we're doing here, these is all just a bunch of power rules. So, 6 times 2, or sorry, 3 times 2 gave us that 6x. We had to do a product rule here, and then over here we had 2 times 30, which gave us 60.
Okay.
Okay. Okay. I'm not going to work out the full problem. I want to give you one little hint on the homework that you're going to, there's one almost that's very, very similar to this on the homework, and I'm going to pull that up real quick. Give me a second. Oh, come on. And then let me just pull this over. There we go. Okay. A manager estimates the daily output of their factory to be Q equals, and then you're given this long expression, where X is the number of unskilled labor hours, and Y is the number of hours of skilled labor and unskilled labor. And it gives you some variables to input, and you're asked to find if we want to maintain the current level of output, where Q is representing that output. That's telling you something without directly telling you something. That is telling you that if we want to, currently the fact, 40, what we have here is that if it's telling you that the output is not changing, that's telling you that dq dt, or the change in output, is going to equal 0. Because in order to maintain the current level of output, we're just going to say dq dt. Okay. And then, we're also told to offset a 1 hour increase in labor. That is telling you that skilled labor, which is X, is telling you that dx dt equals 1. So they're giving you all the information, and then the thing we're looking for is what is dy dt. That's my unknown. And then you're also given that X is 40 and Y is 60. So it's a very, very similar problem. Just sometimes it can be a little hard to interpret. Really, the part that I wanted to emphasize was just this piece right here. That if we're saying that if we're keeping the same level of output, that means that there's no change in output. And no change means that you have a slope of 0. So that's just kind of a little hint for 3.6. It's the last problem, number 8. Okay, folks. That is going to do it for us today. As always, I'll stick around if people have any questions. That quiz is going to go up in 20 minutes. So if you want to start it right after class, it'll be available starting at 8:30 and be available till 6 p.m. tomorrow evening Pacific time. Otherwise, have a lovely evening, and I will see you back here at 6 o'clock tomorrow.
Is it a
Thank
4?
you.